Welcome to the deep dive. So imagine you're designing something really cutting edge, maybe the next big AI thing in your phone, or a super fast trading system. You hit this point, this fundamental question. Do you build a completely custom chip, perfectly optimized, or do you go for something more flexible, something you can change later? Today, we're diving deep into that bedrock of modern electronics.
Awesome.
The ASIC, that's the application-specific integrated circuit, versus the FPGA, the field programmable gate array. We've got this stack of articles and notes you shared, and our mission. Cut through all the jargon, pull out the key nuggets, the surprising stuff, and get you really well-informed fast.
Yeah, it's a choice that honestly shapes so much of the tech we use every single day. And ASIC, basically, it's designed and built for one specific job, period. The circuitry is permanently etched in silicon when it's made. Maximum efficiency, speed, power, size, all optimized.
Right.
But you absolutely cannot change it afterwards.
Right.
Whereas an FPGA, that's more of a general purpose chip. It has this adaptable architecture. You, the designer, can figure it out in the field by loading a digital file, a bit stream. And you can reprogram it for totally different tasks.
Okay, to make that super clear, let's try an analogy. An ASIC is like getting a bespoke suit made by a master tailor. Every stitch, every cut, perfect for one event, one purpose. Amazing performance. Fits like a glove for that gala, let's say. But it's fixed if you suddenly need to, run a marathon in it. Not going to work so well.
Exactly. And if the ASIC is the bespoke suit, the FPGA is more like a high-performance, really adaptable technical jacket. It's got versatile materials, adjustable bits, drawstrings, vents, pockets you can add or remove. You can configure it for hiking one day, maybe skiing the next. It gives you solid performance across different activities. It might not be the absolute peak for any single one, but that versatility, that's its superpower.
So we're looking at this core tension, aren't we? Ultimate optimization for something known and unchanging versus adaptability for things that might evolve, or maybe you don't even know what they'll be yet. It sounds like a constant strategic fight in hardware design.
Oh, it absolutely is a strategic battle. Look, if one was just better overall, the other would have disappeared by now, right? But both are thriving because they serve different needs. ASICs are king, where you have fixed high-volume needs, where every bit of performance or power matters. FPGAs win when you need to get to market fast, when volumes are lower, when you know the design will need updates. It's as much a business decision as a technical one, really.
Okay, right. That makes sense. But what's actually inside them? What makes the suit and the jacket so different under the hood?
Now we get to the interesting part, the architecture. Let's start with the FPGA, the adaptable one. Its core is this malleable fabric. It's made of arrays of what we call configurable logic blocks, or CLBs. Think of them like tiny programmable building blocks, sort of like high-tech Lego bricks. Inside each CLB, you find lookup tables, LUTs. These are basically small bits of memory you program to act like any logic gate you need. And alongside them, flip-flops for storing state, remembering things.
So the CLBs are the Lego bricks. What connects them? That adaptable jacket needs seams.
That's a good point. Surrounding these CLBs is this incredibly rich network of programmable interconnects. Think of it as a dense city grid, but with configurable traffic lights and one-way signs. It's wires and tiny switches that you program to route signals between all those Lego bricks. This flexibility is amazing. It's the FPGA's strength. And this is key, the flexibility comes at a cost. It introduces overhead. Signals often take longer routes, go through more switches compared to a direct wire in an ASIC.
So more potential delays, maybe uses more power too.
Exactly. More delay, higher power consumption. That's the trade-off for being programmable. But wait, modern FPGAs aren't just Cs of these generic blocks anymore. To get better performance, they integrate dedicated silicon blocks too. We call them hard IP cores. These are super efficient for common complex jobs like DSP slices for math-heavy stuff like signal processing, block RAM for fast on-chip memory, high-speed transceivers. These are SerDes blocks for things like PCIe or fast Ethernet. And many newer FPGAs even have hard processor cores like actual ARM CPUs built right in.
Wow. Okay, so FPGAs are becoming almost like mini systems themselves, blurring the lines a bit with ASICs.
You hit it exactly. That's a crucial point. These hardened blocks let FPGAs offer performance that's getting closer to ASICs for those specific functions, but still within that flexible framework. And just quickly, FPGAs also differ in how they store their configuration. Most common are SRAM-based. They need to load the config each time they power up. Then there are flash-based ones, non-volatile, instant-on, and older antifuse types, one-time programmable. Okay, now let's switch to the ASIC. Fundamentally different. It's custom-built, ground up for just one thing. No programmability after it leaves the factory. Most modern ASICs use what are called standard cells. Think of these as pre-designed basic logic building blocks, simple gates, flip-flops from a library provided by the silicon foundry. The granularity is different here. An FPGA LUT might handle a complex function, but an ASIC builds that same function using maybe several simpler standard cells, all wired together perfectly with fixed metal layers, like drawing permanent roads on a map.
Got it. So if the FPGA is the configurable city grid, the ASIC is like a custom-designed high-speed rail network. Fixed routes, super optimized for specific destinations.
Perfect analogy. And just like rail networks vary, ASICs have a spectrum too. You've got full custom, absolute best performance, lowest power, but crazy expensive and time-consuming to design. Then semi-custom, using those standard cells, which is the most common approach, balancing everything. And a huge trend in ASICs is the system on chip, the SoC, packing everything, CPU cores, memory, specialized processors, peripherals, even analog stuff onto one single chip. That's what's in your smartphone, giving you incredible power in a tiny package.
Right, that makes total sense. So these architectural differences, they directly map to the trade-offs we see in performance, power, and just how much space they take up on the silicon. Is that where this 10x rule of thumb people mention for FPGAs comes from?
It absolutely is. That inherent overhead in FPGAs, the memory for the LUTs, all those programmable switches and wires, the configuration memory itself, it all takes up way more silicon space. An ASIC doing the exact same logic function can be, 10 to 20 times smaller. This overhead also means signals travel longer paths, leading to slower speeds, and all those extra transistors burning power mean higher power consumption. ASICs are lean. Only the necessary stuff is there. And while FPGAs keep getting better, adding those hard blocks helps. That fundamental cost of programmability, maybe around 10x in area, power, or speed penalty compared to a pure custom solution, that's still a pretty persistent factor.
Okay, time for the head-to-head. Raw speed, power draw, physical size, who takes the crown in these categories?
Well, for pure speed and data throughput, ASICs generally have a clear edge. They can run at clock frequencies that are typically, let's say, 3 to 4 times higher than an equivalent FPGA. Why? Because the connections are optimized, shorter, dedicated, no navigating that programmable grid. This means lower latency 2 signals get where they're going faster. And overall data throughput can be significantly higher, maybe 5 to 10 times faster than what you'd get from an FPGA doing the same job. That's why they're essential for things like high-end network switches, super fast trading systems, or those dedicated crypto mining rigs.
Speed demons. Got it. What about power consumption? Who's more efficient?
ASICs win on efficiency too, usually by a significant margin. FPGAs, especially the common SRAM-based ones, they burn a noticeable amount of static power. That's leakage from all the configuration memory and interconnects, even when they're just sitting there idle. ASICs have much lower static power because, well, they only contain the circuits they actually need. And dynamic power, the power used when things are switching. ASICs typically use 5-10 times less than FPGAs. That's thanks to optimizing transistor sizes, having shorter wires, which means less capacitance to charge and discharge, and simply not having any extra circuitry switching unnecessarily. So overall, ASICs deliver much higher performance per watt.
And area, the actual silicon footprint.
Again, ASICs are much smaller, typically 10 to 20 times less silicon area for the same amount of logic. FPGAs just need all that extra room for the programmable bits and the routing channels. That smaller size means the individual ASIC chip is cheaper to manufacture, and you can pack more functionality onto one chip. Plus, ASICs find it easier to integrate things like analog components or specialized I/O directly onto the same die. So I guess FPGAs have made huge leaps with hard blocks like DSPs and high-speed SerDes, mitigating some disadvantages, and ASIC can optimize the entire data path, every single connection. That maintains a decisive edge when you're pushing the absolute limits of performance or power efficiency.
Okay, so we've covered the raw specs, speed, power, size. ASICs generally lead there. But hardware isn't just about the silicon itself, is it? What about getting products out the door quickly and adapting once they're out there? That feels like where the story might flip.
It absolutely does. And this is where FPGAs play their trump card. Reprogrammability, it's their biggest advantage. You can change the hardware logic, fix bugs, add new features, just by loading a new configuration file, a new bit stream, even after the product's been shipped and is running in the field. This allows for incredibly fast iteration during development. You find a problem, you fix it in code, recompile, test again, maybe in hours. Now contrast that with an ASIC. Once it's fabricated, it's immutable, set in stone, or rather silicon. If you find a bug after manufacturing a silicon bug, you're looking at a respin.
A respin sounds expensive.
Oh, it is. Very. It means correcting the design files, ordering a whole new set of incredibly expensive photomasks, and going through the entire weeks or months-long fabrication process again. It adds months to your schedule and often millions of dollars to the cost. It's a nightmare scenario for ASIC teams.
Wow. Okay, so time to market must be a massive win for FPGAs then.
Huge win. FPGAs let you get a product to market much, much faster, often in, say, 3 to 6 months. Because they're off-the-shelf parts. You buy the chip, you program it, done. ASIC development, much longer. You're typically looking at 12 to 24 months, sometimes even more, because of all the design, the intense verification, and then the fabrication time itself. In fast-moving markets, or when getting that first-mover advantage is critical, that FPGA TTM advantage can literally make or break a product.
Right, but there must be a point where the ASIC becomes cheaper overall, right? Especially if you're making millions of them. That brings us to production volume.
It's exactly the economic tipping point. FPGAs are usually more cost-effective for lower to medium production volumes. Why? Because they have very little or zero non-recurring engineering NRE costs tied directly to making the chip itself. ASICs, however, have massive NRE costs up front. But once you get to high production volumes, you can spread that huge NRE cost over many, many units. That makes the cost per chip for an ASIC significantly lower than an FPGA in large quantities. Where that crossover point happens, well, it varies a lot. Depends on the complexity of the chip, the cost of the FPGA versus the projected ASIC cost. It could be a few thousand units for simple designs, or maybe tens of thousands, even hundreds of thousands for really complex ones.
Can you give a rough example?
Sure. Let's say you have a fairly simple FPGA costing $15. The equivalent ASIC might cost only $2 per unit, but maybe has an NRE of $50,000. The break-even point there is around 3,800 units. But for a complex high-end FPGA costing maybe $500 versus an ASIC at $50 per unit, but with a massive $2 million NRE, the break-even is closer to 4,400 units. So you see, it's not a simple rule. You have to run the numbers for your specific case.
And that flexibility you mentioned, the reprogrammability, it's not just about fixing bugs during development, is it? How important is that after the product is out there?
Oh, it's incredibly important. That post-deployment adaptability is vital for many products. Think about things with long lifespans, like satellites or industrial equipment, or products that need to keep up with changing standards like 5G or Wi-Fi protocols, or security algorithms, or just needing to fix bugs found later in the field. Imagine updating satellites remotely to use a new communication scheme, or medical devices getting new algorithms to analyze patient data better, or, a really big one now, AI accelerators getting updated with completely new machine learning models as the research advances. This future-proofing capability is a huge benefit. It's hard to put an exact dollar value on it, but it can extend product life, save on costly hardware replacements, and keep products competitive. It means you have to think about uncertainty and future needs when you make that initial ASIC versus FPGA choice.
Okay, let's really dig into the money side now. The bottom line, these financial implications, especially the NRE you mentioned, they seem enormous.
They really are. NRE, non-recurring engineering costs, that's all the upfront money you spend before you make even the first production chip. For ASICs, this is where it gets really eye-watering. You've got large design and verification teams, their salaries, the licenses for the electronic design, automation, EDA software, which are incredibly expensive, potentially millions per year. You might need to license intellectual property, IP blocks from other companies. And then the big one, the photomask set. For manufacturing the chip, we're talking maybe hundreds of thousands of dollars for older, less complex process nodes. But for modern ones, it easily jumps over $10 million for something like a 7-nanometer chip, and cutting-edge 3-nanometer masks could be pushing $40 million.
Just for the masks.
$40 million just for the masks. Wow. Yep. Then add costs for the initial tape-out submission to the foundry, prototype wafer runs, developer the test programs. Total ASIC NRE easily runs into the millions, and for complex chips at the leading edge, hundreds of millions isn't unheard of.
That is staggering. So how does FPGA NRE compare? Is it negligible?
Compared to ASIC NRE, yeah, it's much, much lower. Your main FPGA NRE costs are things like the development tool licenses, which are still significant, but way less than ASIC tools buying development boards to test on. And of course, the engineering time to write the code and test it. But crucially, you pay zero direct photomask or chip fabrication NRE because the FPGA chip itself is already manufactured by Xilinx or Intel or whoever. You're just buying an off-the-shelf part. So you have this dynamic. ASICs have that massive upfront NRE hurdle, but achieve very low per unit cost if you make enough of them. FPGAs have low upfront NRE, but their per unit cost is inherently higher and doesn't drop nearly as much with volume.
So that huge ASIC NRE really acts like a gatekeeper, doesn't it? It limits who can even consider playing the ASIC game.
Absolutely. It's a major economic gatekeeper. It reserves ASICs primarily for those high-volume products where the performance or power savings are so critical they justify that massive upfront gamble. And it makes the financial risk of needing a respin absolutely terrifying.
Which brings us back to that FPGA to ASIC strategy. Start with the lower risk FPGA.
Exactly. It's become a very common, very sensible strategy. Develop your product using an FPGA, get to market quickly, test the waters, see if customers actually want it, refine the design based on real-world feedback, all with relatively low financial risk. Then, if the product is a hit and the volumes start ramping up, then you invest the big bucks to convert the design into an ASIC to get those lower per unit costs and potentially better performance for mass production. It de-risks the whole process significantly. The financial angle often dictates the entire strategy.
Okay, let's unpack the actual journey. How do you design these things? What are the steps, the tools, the key differences in the process from concept to actual silicon or, the FPGA bitstream?
Right, the design flow. The FPGA flow is generally geared towards speed and iteration. You start with your system specification, what does it need to do? Then design entry, usually writing hardware description language, HDL code Verilog or VHDL are the main ones. Or maybe using high-level synthesis, HLS, writing in C or C++ flat. That code goes into synthesis. This is where the FPGA vendors' tools like Xilinx Vivado or Intel Quartus translate your description into a netlist, basically a list of connections, using the FPGA's specific building blocks, those LUTs and flip-flops we talked about. Next is place and route, or P&R. This step takes that netlist and figures out exactly where to put each logic element on the physical FPGA chip and how to connect them using that programmable interconnect grid. Finally, the tools generate the bit stream. That's the binary file you actually load onto the FPGA to make it do its job.
And the crucial part here is testing and debugging, right? You can actually try it out quickly.
Precisely. You do simulations of your HDL code first, of course. But the real power is in circuit testing. You load the bit stream onto a real FPGA on a development board and use tools like Xilinx ChipScope or Intel SignalTap to actually probe signals inside the running chip. The iteration cycle is fast. Find a bug, tweak the code, resynthesize, replace and route, generate a new bit stream, test again. This can often be done in minutes or hours. It encourages experimentation. Now, the ASIC design flow, much more involved, much more rigorous. Because of that permanence and the cost of mistakes, the system specification has to be incredibly thorough and stable up front. Late changes are disastrously expensive. Then there's usually a dedicated architectural design phase, figuring out the high-level structure. Logic design, RTL, follows, writing the detailed HDL. Then comes verification. This is the big one for ASICs.
You said 60–80% of the effort?
Easily, sometimes more. It's the most critical phase. You use extensive simulations, maybe formal verification using mathematical methods to prove correctness, gate-level simulations after synthesis, static timing analysis, STA, to ensure it meets speed requirements. For really complex chips, you might even build an emulator using FPGAs to run tests faster than simulation. Anything to catch bugs before you make silicon.
Makes sense. Kill the bugs before they get expensive. What happens after this massive verification effort?
Then you move to physical design, or layout. This turns the verified netlist into the actual geometric patterns that will be etched onto the silicon wafer. It involves steps like floor planning, arranging major blocks, placement, placing millions of standard cells, clock tree synthesis, distributing the clock signal perfectly, and routing, connecting everything with metal wires. After layout, there's more verification. Physical verification, checking against the foundry's manufacturing rules, DRC, making sure the layout matches the schematic, LVS, checking for electrical issues, ERC. Only when everything passes, you get sign-off. Then, tape out.
Tape out, the point of no return you mentioned.
Exactly. The design data is finalized and sent to the semiconductor foundry. The design is frozen. Manufacturing begins, which takes weeks or months. Then the finished wafers are tested, chips are cut out, packaged, and final testing happens.
Wow. Comparing those flows, the ASIC process just sounds orders of magnitude more complex and stressful. The verification burden alone is huge.
It is. And that tape-out milestone hangs over everything. The pressure to get it right the first time is immense because a respin costs millions in months. It forces a very cautious, verification-heavy methodology. Contrast that with the FPGA's fast feedback loop. It lets you try things, innovate more freely, prototype ideas quickly, like new AI algorithms where you're not even sure the approach will work yet. FPGAs are fantastic for that kind of exploratory development or getting a minimum viable product out fast. The flow profoundly shapes how you approach design and manage risk.
So what tools are in the designer's toolbox for these very different processes? What software makes this happen?
Well, the common language for both is usually a hardware description language, or HDL. Verilog and VHDL have been the standards for decades. System Verilog, which is an extension of Verilog, is heavily used now, especially for the complex verification needed in ASICs. These languages let you describe the digital circuits. For FPGAs, the tool chains are mostly provided by the FPGA vendors themselves. The big ones are AMD Xilinx with their Vivado design suite and Intel with Quartus Prime Design software. These are big integrated environments, IDEs, highly optimized for their specific FPGA chips. They handle synthesis, place and route, bitstream generation, debugging, IP integration, often HLS too. There are also some third-party tools for synthesis, like from Siemens EDA or Synopsys, and simulation tools like ModelSim. And interestingly, there's a growing open-source movement for FPGA tools, things like Yosys for synthesis and NextPNR for place and route, especially for some of the smaller or older FPGA families. It's making things more accessible.
And the ASIC tools, given the complexity and cost, I imagine they're a different beast entirely.
Well, yeah, ASIC electronic design automation, EDA, is dominated by just a few large companies: Synopsys, Cadence Design Systems, and Siemens EDA. The reason is the sheer R&D investment needed to create tools that can handle billions of transistors on the latest, most complex manufacturing processes. We're talking tools that cost millions of dollars per license per year. These suites cover everything: design entry, advanced RTL synthesis, extremely sophisticated simulation and verification environments, often using standardized methodologies like UVM, tools for inserting test structures, DFT, and generating test patterns, ATPG, the incredibly complex physical implementation tools for place and route and clock tree synthesis, and finally the sign-off verification tools for timing, STA, and physical rules, DRC, LVS, ERC, plus specialized tools for custom layout or analog design if needed.
It really sounds like the tools perfectly mirror the hardware philosophy. ASIC tools for absolute precision and managing immense complexity, FPGA tools more focused on usability and speed for a predefined platform.
That's a great way to put it. The cost and specialization of ASIC EA tools reflect that get it right the first time, necessity. FPGA tools are generally more accessible, sometimes even free or open source for smaller devices. High-level synthesis, HLS, is a trend impacting both letting engineers write C++ or System C and have tools generate the HDL. It aims to boost productivity for complex algorithms, but you still need to understand the hardware implications, and the quality of the generated logic can vary. Tool choice really comes down to your target chip, the design's complexity, performance goals, and of course, your budget.
Okay, so we've covered architecture, performance, cost, tools, the whole design process. Let's bring it all together. For someone facing this choice in a real project, how do they decide? When is an ASIC the right call, and when should they stick with an FPGA? It feels like more than just ticking boxes on a spec sheet.
It absolutely is. It's a strategic decision with multiple dimensions. Let's recap the key factors. Performance. Need the absolute highest speed, lowest latency, maximum throughput. ASIC is likely your answer. FPGAs are good for moderate to high performance, especially using those built-in hard blocks. Power consumption. Got a tight power budget, like in a battery-powered device. ASICs are significantly more power efficient. FPGAs are better than CPUs or GPUs for certain tasks, but still use more power than an ASIC. Production volume. Low to medium volumes. FPGA usually makes more economic sense. High to very high volumes. ASIC becomes cheaper per unit, justifying the NRE. Upfront cost, NRE. Can you afford millions in upfront investment? ASIC might be feasible. Need to keep initial costs low. FPGA is the way to go per unit cost. Focused on minimizing cost per device in mass production. ASIC wins after NRE. Less sensitive to per unit cost, especially at lower volumes. FPGA is fine. Time to market. Need to launch ASP. FPGA is dramatically faster months versus years for an ASIC. Flexibility and reconfigurability. Do you expect requirements to change? Need to fix bugs or add features after launch? Need to adapt to evolving standards. FPGA is essential. ASIC is fixed. Design complexity and team. Tackling something huge and complex, you'll need a large, specialized ASIC team. FPGAs can often be handled by smaller teams for many projects. Risk tolerance. How much financial risk can you tolerate? FPGAs are lower risk, easier, cheaper to fix mistakes. ASIC design carries significant financial risks due to costly respins.
That's a great summary. So putting that into practice, where do we typically see FPGAs being used?
Okay, common FPGA use cases. Definitely prototyping and emulation of ASICs, build it on an FPGA first to test it. Low to medium volume production runs. Products where standards or algorithms change frequently, think 5G, 6G infrastructure. AI accelerators where models evolve, a lot in R&D labs. Hardware acceleration for tasks like data analytics, video processing, financial modeling. Aerospace and defense love them for adaptability and long life cycles. Also embedded systems, medical devices where updates might be needed.
And ASICs, where are they the undisputed champions?
ASICs really dominate the high-volume, high-performance, low-power areas. Think mass-market consumer electronics, smartphones, tablets, cameras, TVs, gaming consoles, all have multiple ASICs inside. Automotive is huge for ASICs engine control units, ECUs, advanced driver assistance systems, ADS, infotainment, networking and telecom infrastructure. The core routers and switches handling internet traffic rely heavily on ASICs. Big data centers and high-performance computing, especially for custom AI accelerators like Google's TPUs, cryptocurrency mining hardware, almost exclusively ASICs now, and anywhere with extreme power or size constraints, small IoT sensors, medical implants.
Right, so it comes back to that hybrid strategy again, FPGA first, maybe convert to ASIC later if the volume justifies it.
Yeah, that FPGA first, then ASIC approach is often the best way to navigate these trade-offs. Launch fast with an FPGA, validate the market, refine the design. If it takes off, then make the ASIC investment for cost reduction and optimization at scale. It dramatically reduces the upfront risk.
So the choice isn't just technical specs versus cost. It's deeply tied into the company's business strategy, risk profile, and market goals.
Exactly. A startup might lean heavily on FPGAs to get a product out quickly and iterate, minimizing initial investment. A huge company like Apple or Samsung will use ASICs extensively to achieve maximum performance and efficiency at massive scale, leveraging their ability to fund the NRE. That FPGA to ASIC path is a key tool for managing risk, proving the design works, and that people want to buy it before you bet the farm on a multi-million-dollar ASIC development.
Okay, so the chip is designed, maybe it's even launched. What about the longer-term realities, the hidden risks, reliability concerns, and adapting to whatever the future throws at it?
Yeah, that's crucial. Despite all the intense verification that goes into ASICs, the complexity is just so high now that things can still go wrong. Functional bugs can slip through, or sometimes there are subtle manufacturing issues. The sobering reality is, ASIC respins are pretty common. Industry surveys vary, but numbers like 76% of ASIC projects requiring at least one respin aren't unusual. Some studies show first-pass success rates down in the teens, like 14%.
76% need a respin. That's way higher than I would have guessed. The pressure must be unbelievable.
It is, and the consequences are severe, as we said. Millions of dollars down the drain, months added to the schedule, maybe missing your market window entirely, damage to the company's reputation. It reinforces that get it right the first time pressure immensely. And this is where FPGA reprogrammability shines again, acting as that vital safety net. You find a bug after shipping thousands of units. With an FPGA, you can often develop a fix, test it, and deploy it remotely via a firmware update. You avoid a costly hardware recall.
And you mentioned bugs getting out are common even with FPGAs.
Yeah, one study I saw suggested something like 84% of FPGA designs have non-trivial bugs that actually escape verification and make it into production systems. Being able to fix those in the field is huge. Beyond bug fixes, it enables those feature enhancements, adapting to new communication protocols or security standards, deploying improved AI models. Think updating scientific instruments on Mars, or refining algorithms in medical scanners or self-driving cars based on new data, or patching security vulnerabilities. Security itself is another angle. FPGAs have potential vulnerabilities around the bit stream. It needs to be encrypted and authenticated properly to prevent cloning or tampering. SRAM-based FPGAs can also be susceptible to radiation effects, causing bit flips, SEOs, needing mitigation like redundancy. ASICs, being custom, can integrate very robust hardware security features, secure boot, crypto accelerators, physical unclonable functions. They're harder to reverse engineer physically, but they face a growing threat from counterfeit chips, fraudulently marked, salvaged, or cloned parts that might have reduced performance, poor reliability, or even hidden backdoors.
So hearing about those high ASIC respin rates and the prevalence of bugs even in FPGA designs, how does that change the whole cost-value equation?
It fundamentally shifts it. You can't just look at the initial NRE quote for an ASIC anymore. You realistically have to factor in the probability and cost of needing one or maybe even two respins. Suddenly, the higher per unit cost of an FPGA looks a lot more attractive if it helps you avoid even one multi-million-dollar respin cycle. And that future-proofing value of FPGA reconfigurability, it's not just a nice-to-have, it's a real strategic asset. It can extend the useful life of a product significantly, delaying the need for a whole new hardware redesign. It allows companies to respond faster to market changes, new competitor features, or emerging security threats. So a truly comprehensive decision requires assessing risk and valuing adaptability, moving beyond just the static snapshot of initial cost and performance.
So wrapping this all up, what's the takeaway for the future of hardware? This ASIC versus FPGA landscape seems dynamic, definitely not static.
That's exactly right. The core trade-off isn't going away. ASICs for that deep custom optimization when you need peak performance or efficiency at scale. FPGAs for flexibility, faster time to market, and reprogrammability. That FPGA first, then ASIC strategy. It's become a standard, prudent approach for managing risk and cost for many new products. And we're definitely seeing the lines blur. FPGAs are becoming more powerful, more ASIC-like by integrating more and more hard IP blocks, powerful processors, complex I/O, large memories, dedicated AI engines. They're tackling true system-on-chip designs now. And from the other side, you have things like structured ASICs trying to bridge the gap, offering some pre-verified blocks combined with customizable logic, aiming for lower NRE and faster turnaround than traditional ASICs.
And what about the really big trends? Things like AI actually helping design these complex chips or new ways of packaging them.
Yeah, those are huge. The integration of AI and machine learning into the EDA tools themselves is happening now. Trying to use AI to help manage the insane complexity, maybe optimizing synthesis or place and route automatically, or making verification smarter and faster. And the rise of chiplet technology and advanced packaging is really exciting. Instead of one giant monolithic chip, you connect smaller, specialized chiplets together in one package. This could let you mix and match, maybe use an ASIC chiplet for the core high-performance processing, connected to an FPGA chiplet for flexible I/O, or features that might change. It opens up possibilities for hybrid systems that truly blend the strengths of both worlds.
So as everything gets exponentially more complex, AI, IoT, 5G, 6G, autonomous everything, what does that mean for our ability to actually design this stuff, that productivity gap people talk about?
It means the gap between what we can imagine building and our ability to actually design, verify, and manufacture it efficiently is widening. It's a massive challenge. And frankly, neither traditional FPGAs nor traditional ASICs, as we know them today, might be the perfect answer for all the challenges ahead. We're almost certainly going to see continued evolution, maybe even radically new hardware paradigms emerge that find clever ways to blend the best of custom hardware's efficiency with programmable logic's flexibility. So the final thought maybe is this: the right choice between ASIC and FPGA for a specific application today. Well, it might be a completely different calculation tomorrow. As the technologies evolve, the tools get smarter, and the system requirements keep exploding. Staying constantly aware of these shifts, these evolving capabilities and methodologies, that's going to be absolutely crucial for anyone working at the cutting edge of hardware.